Today we will talk about Fibonacci numbers. The Fibonacci sequence is defined in the following way. So the number f1 is defined as 1, f2 is defined as 1, and each subsequent Fibonacci number, fn plus 1, is defined as a sum of fn and fn minus 1. So we can extend this sequence by saying that f3 is equal to 1 plus 1, that's 2. f4 is 1 plus 2, that's 3. f5 is 2 plus 3, that's 5. f6 is 3 plus 5, that's 8. f7 is 5 plus 8, that's 13. f8 is 8 plus 13, 21. And f9 is 13 plus 21, that's 34. And f10 is 55, and so on. So what we want to do is we want to find a formula for fn. And for example, we want to determine how many decimal digits in f1000. Fibonacci sequence was introduced by Fibonacci 500 years ago in his study of the growth of a population of rabbits. The challenge in working with Fibonacci numbers is that the next Fibonacci number is determined not by the previous one, but the sum of the two previous Fibonacci numbers. We are going to solve these problems using linear algebra. And this may look surprising, because as this problem is stated, there is no view of linear algebra inside. The key observation here is that we can overcome this difficulty of the definition of Fibonacci numbers using vectors. To do this, so we set the following sequence of vectors. So let's call Wn to be a two-component vector, where the first component is fn and the second component is fn plus 1. Now let us write the expression for Wn plus 1. So here Wn plus 1 will be a two-component vector where the first component is fn plus 1 and the second component is fn plus 2. But we know that each next Fibonacci number is a sum of two previous ones. So this can be written as fn plus 1 and the sum of fn and fn plus 1. And now we see that the expressions that appear here are the components of the previous vector Wn. So what we want to do is we can write this expression as some matrix multiplied by the vector Wn. So this is fn and fn plus 1. Now let us determine this matrix. The first component of this product will be the dot product of the first row of this matrix with this column. And we need to get fn plus 1. So this means that the first row should be chosen as 0, 1. So then the dot product of 0, 1 with fn plus 1 will give us fn plus 1. And then to get in the second component fn plus 1, we obviously need to take as a second row 1, 1. So then the dot product of 1, 1 with fn plus 1 will be precisely this sum. And so what we see is that the next vector in this sequence is the product of this matrix with the previous vector in the sequence. So if we call this matrix A, then our relation is Wn plus 1 is A times Wn. It will be convenient for us to start this sequence with index 0. And then for this pattern to work, we see that f0 should be defined as 0. So then f2 is the sum of two previous elements, so 0 plus 1 is equal to 1. Then we have that the vector w0 is the vector 0, 1. And our relation is wn plus 1 is equal to a times wn. So this is what we gained by going to vectors. Now each subsequent vector is defined only by the previous vector in this sequence. So then we have that w1 is equal to a times w0, w2 is a times w1, but w1 is a times w0. So we get that a times w0. So this is a squared times w0. And w3 is equal to a times w2. And w2 is a squared times w0. So we get that w3 is a cubed times w0. And now we can see the pattern that the vector wn, which is fn plus 1, is equal to a to the power n applied to w0, where a is this matrix. How can we compute nth power of a matrix? It turns out that the answer to this question is given by the diagonalization procedure. We have the following lemma. If A is equal to C, D, C inverse, then A to the power n is equal to C, D to the power n times C inverse. So let us prove this. So when we write A to the power n, so this is n factors of A, and A is equal to C, D, C inverse. So we have C, D, C inverse times C, D, C inverse times C, D, C inverse dot C, D, C inverse. And we have n factors of this. But here in the middle, factors C inverse and C will cancel. So everywhere in the middle. And so what we will end up with is we have the first factor of C, then we have n factors of D, and the last factor of C inverse that will survive. And that's the formula that we have. So why does this lemma makes us any happier? So still here we have to compute D to the power n, and we also have this extra factor of C and C inverse. So if D is the diagonal matrix, and we know that in the diagonalization procedure we get a diagonal matrix with eigenvalues on the diagonal and zeros elsewhere, then we know that when we multiply diagonal matrices, then the entries on the diagonal will multiply. And because of this, we will have that D to the power n is again a diagonal matrix with the powers of the eigenvalues on the diagonal. So then, using diagonalization procedure and this lemma, we can calculate nth power of a matrix A. Let us carry out this plan. So let us take this matrix and diagonalize it. The characteristic polynomial for a 2 by 2 matrix is given by expression. It's lambda squared minus trace of A times lambda plus determinant of A. For this matrix, we have that trace is equal to 1. So we have lambda squared minus lambda, and determinant is equal to minus 1. So this will be the characteristic polynomial. Now let us solve the quadratic equation to find the roots of the characteristic polynomial. So here we will have 1 plus minus square root of b squared minus 4ac. So this is going to be 5, and all divided by 2. And we get two roots. Lambda 1 is 1 plus square root of 5 over 2, and lambda 2 is 1 minus square root of 5 over 2. By the way, this first eigenvalue here is a golden ratio. Since we know the roots, this characteristic polynomial may be factored. It's lambda minus lambda 1 times lambda minus lambda 2. So if we expand this, then we get lambda squared minus, so the coefficient at lambda will be lambda 1 plus lambda 2 and times lambda. And the constant term will be lambda 1 times lambda 2. From here, we can see some properties of this pair of numbers. So that lambda 1 plus lambda 2 is equal to 1. Well, that's easy to see. But what's more interesting, and that we will use later on, is that the product of these two eigenvalues is equal to negative 1. Let us now find the eigenvectors. And we begin with eigenvalues lambda 1, which is 1 plus square root of 5 over 2. So we have to compute the kernel of the matrix A minus lambda 1 times identity matrix. So we take matrix A and subtract lambda 1 from the diagonal entries. So we get negative lambda 1, 1, 1, and 1 minus lambda 1. But here we know that lambda 1 plus lambda 2 is equal to 1. And because of this, 1 minus lambda 1 is equal to lambda 2. And so what we get is we get the matrix minus lambda 1, 1, 1, lambda 2. Let us carry out row reduction. So first we switch rows 1 and 2. And we get the matrix 1, lambda 2, minus lambda 1, and 1. And next, we are going to say that new row 2 is row 2 plus lambda 1 times row 1. So then this gives us the new matrix 1, lambda 2, 0. And here we get 1 plus lambda 1 times lambda 2. But lambda 1 times lambda 2 is equal to negative 1. And so this means that this is going to be 0. And as predicted, we get the reduced form, which has a row of zeros. Now we can write down the solution vector, x1, x2. So we assign parameter t to the free variable x2. And then x1 is going to be minus lambda 2 times t. So this is t times the vector minus lambda 2, 1. And this gives us the eigenvector v1 is negative lambda 2, 1. Next, we would like to find the eigenvector for the second eigenvalue, lambda 2, which is 1 minus square root of 5 over 2. And here we will use the following trick. If our matrix has rational, or in this case, integer coefficients, and one of the eigenvalues contains an irrational square root, like here we have square root of 5, which is an irrational number, then eigenvalues will come in conjugate pairs. So here, if we change the sign at the square root of 5, so then one eigenvalue will turn into another eigenvalue. So by switching the sign of the square root, we will go from one eigenvalue to another one. And then the same procedure works for eigenvectors as well. So if we have calculated the first eigenvector, then by switching the sign at the square root of 5, we will go from one eigenvector to the second eigenvector. And here we have lambda 2, and switching the sign of the square root of 5 in lambda 2 will give us lambda 1. So this tells us that the second eigenvector will be minus lambda 1 and 1. I recommend that you carry out the calculation of the second eigenvector explicitly, and then see that the difference between the computation of v1 and the computation of v2 will be indeed switching the signs at square root of 5 everywhere in your calculation. Now we get the basis of eigenvectors. So the first basis vector v1 is negative lambda 2, 1, and the second basis vector v2 is negative lambda 1, 1. This gives us the change of basis matrix, so which is the matrix of base of change from basis B to the standard basis. So here we place our eigenvectors as columns. So we have minus lambda 2, 1, minus lambda 1, 1. And we have the diagonal matrix D, where we have eigenvalues on the diagonal. So the first eigenvector v1 has eigenvalue lambda 1, and the second eigenvector has eigenvalue lambda 2. For our diagonalization formula, we also need to know the inverse of the change of basis matrix C. And here we point out that determinant of the matrix C is equal to minus lambda 2 plus lambda 1. And this is, so lambda 1 minus lambda 2, so this equals square root of 5. Then for 2 by 2 matrices, we have a nice formula for the inverse of a 2 by 2 matrix. So it's 1 over the determinant of C times the matrix D minus B minus C A. So in our case, we get 1 over square root of 5 times the matrix. So we get 1, then lambda 1, minus 1, and minus lambda 2. And now we can assemble everything together. So we see that the vector fn plus 1, is equal to a to the power n times w0, or this is c times d to the power n times c inverse times w0. Or in terms of matrices, so this will be matrix C, which is minus lambda 2, minus lambda 1, 1, 1, times d to the power n. So this is lambda 1 to the power n, 0, 0, lambda 2 to the power n, times C inverse, which is 1 over square root of 5, times the matrix 1, lambda 1, minus 1, minus lambda 2, times the vector w0, which is 0, 1. Let us multiply the first two factors and the last two factors, and we put 1 over square root of 5 in front. So the first product will be, so we take dot products of first row with first column. So here we get minus lambda 2 times lambda 1 to the power n. Then here we get minus lambda 1 times lambda 2 to the power n. So here we will get lambda 1 to the power n and lambda 2 to the power n. And when we multiply this matrix by 0, 1, we are going to get the second column of this matrix. So times the vector lambda 1 minus lambda 2. We can simplify the first matrix, taking into account that the product of lambda 1 with lambda 2 is equal to negative 1. So here we get 1 over square root of 5 times the matrix. So here lambda 1 with lambda 2 will annihilate and take away this negative sign. So we get lambda 1 to the n minus 1. Here we're going to get lambda 2 to the n minus 1. And here we get lambda 1 to the power n and lambda 2 to the power n. And this is being multiplied by the vector lambda 1, negative lambda 2. And we get the vector with the following components. So we have 1 over square root of 5 times the first component is going to be lambda 1 to the power n minus lambda 2 to the power n. And the second component is lambda 1 to the n plus 1 minus lambda 2 to to the power n plus 1. And since this is equal to the column vector fn plus 1, by extracting the first component, we get a formula for the nth Fibonacci number. Fn is equal to 1 over square root of 5 times lambda 1 to the power n, so which is 1 plus square root of 5 over 2 to the power n, minus lambda 2 to the power n, which is 1 minus square root of 5 over 2 to the power n. We point out that lambda 1 is greater than 1, whereas lambda 2 is negative, and the absolute value of lambda 2 is less than 1. So this tells us that as n increases, the first term becomes dominant, whereas the second term will go to 0 in the limit. So what we see is that the Fibonacci number may be obtained by rounding just the first term. So 1 over square root of 5 times 1 plus square root of 5 over 2 to the power n. So this number is never an integer, but for large n, it will be ever closer and closer to integers that are nth Fibonacci numbers. So here we see this interesting relation between Fibonacci numbers and the powers of a golden ratio. So let us see, what is the number of decimal digits in F1000? So here we compute log base 10 of F1000. So this approximately equals, so we take log base 10 of this number. So we get 1000 times log base 10 of 1 plus square root of 5 over 2 minus logarithm base 10 of square root of 5. So 1/2 log base 10 of 5. So this is approximately 208.987 minus 0.349. So we see that log base 10 of F1000 is between 208 and 209. And this tells us that the Fibonacci number with index 1000 has 209 decimal digits.